In mathematics, the Killing form, named after Wilhelm Killing, is a symmetric bilinear form that plays a basic role in the theories of Lie groups and Lie algebras. History and name. The Killing form was essentially introduced into Lie algebra theory by L. Cartan in his thesis. The name Killing form first appeared in a paper of Almond Borel in 1951, but he stated in 2001 that he doesn't remember why he chose it. Borel admits that the name seems to be a misnomer, and that it would be more correct to call it the Cartan form. Wilhelm Killing had noted that the coefficients of the characteristic equation of a regular semi-simple element of a Lie algebra is invariant under the adjoint group, from which it follows that the Killing form is invariant, but he did not make much use of this fact. A basic result Cartan made use of was Cartan's criterion, which states that the Killing form is non-degenerate if and only if the Lie algebra is a direct sum of simple Lie algebras. Definition. Consider a Lie algebra G over a field K. Every element X of G defines the adjoint endomorphism AD of G with the help of the Lie bracket, as now, supposing G is of finite dimension. The trace of the composition of two such endomorphisms defines a symmetric bilinear form with values in K, the Killing form on G. Properties. The Killing form B is bilinear and symmetric. The Killing form is an invariant form, in the sense that it has the associativity property, where is the Lie bracket. If G is a simple Lie algebra, then any invariant symmetric bilinear form on G is a scalar multiple of the Killing form. The Killing form is also invariant under automorphisms S of the algebra G, that is, for S in AUT. The Cartan criterion states that a Lie algebra is semi-simple if and only if the Killing form is non-degenerate. The Killing form of a nilpotent Lie algebra is identically zero. If I, J are two ideals in a Lie algebra G with zero intersection, then I and J are orthogonal subspaces with respect to the Killing form. The orthogonal complement with respect to B of an ideal is again an ideal. If a given Lie algebra G is a direct sum of its ideals I1 in, then the Killing form of G is the direct sum of the Killing forms of the individual summands. Matrix elements. Given a basis A of the Lie algebra G, the matrix elements of the Killing form are given by where IAD is the Dynkin index of the adjoint representation of G. Here in Einstein's summation notation, where the Cij are the structure coefficients of the Lie algebra, the index K functions as column index and the index N as row index in the matrix ADAD, taking the trace amounts to putting K equals N and summing. And so we can write the Killing form as the simplest two-tensor that can be formed from the structure constants. In the above index definition, we are careful to distinguish upper and lower indices. This is because, in many cases, the Killing form can be used as a metric tensor on a manifold, in which case the distinction becomes an important one for the transformation properties of tensors. When the Lie algebra is semi-simple over a zero-characteristic field, its Killing form is non-degenerate, and hence can be used as a metric tensor to raise and lower indexes. In this case, it is always possible to choose a basis for G such that the structure constants with all upper indices are completely antisymmetric. The Killing form for some Lie algebras G are connection with real forms. Suppose that G is a semi-simple Lie algebra over the field of real numbers. By Cartan's criterion, the Killing form is non-degenerate, and can be diagonalized in a suitable basis with the diagonal entries plus or minus 1. By Sylvester's law of inertia, the number of positive entries is an invariant of the bilinear form, i.e., it does not depend on the choice of the diagonalizing basis, and is called the index of the Lie algebra G. This is a number between 0 and the dimension of G, which is an important invariant of the real Lie algebra. In particular, a real Lie algebra G is called compact if the Killing form is negative definite. Note that this is one of two inequivalent definitions commonly used for compactness of a Lie algebra. The other states that a Lie algebra is compact if it corresponds to a compact Lie group. The definition of compactness in terms of negative definiteness of the Killing form is more restrictive, since using this definition it can be shown that under the Lie correspondence, compact Lie algebras correspond to compact Lie groups. If GC is a semi-simple Lie algebra over the complex numbers, then there are several non-isomorphic real Lie algebras whose complexification is GC, which are called its real forms. It turns out that every complex semi-simple Lie algebra admits a unique compact real form G. The real forms of a given complex semi-simple Lie algebra are frequently labeled by the positive index of inertia of their Killing form. For example, the complex special linear algebra SL has two real forms, the real special linear algebra, denoted SL, and the special unitary algebra, denoted SU. The first one is non-compact, the so-called split real form, and its Killing form has signature. The second one is the compact real form and its Killing form is negative definite, i.e., has signature. The corresponding Lie groups are the non-compact group SL of 2 times 2 real matrices with the unit determinant and the special unitary group SU, which is compact.